Assalamualaikum warahmatullahi wabarakatuh. I'm Achmad Hashfi Mawarid, student number 83. Process design. Many chemical engineers feel that process design is the most interesting kind of work in their profession. Certainly, the training chemical engineers receive in college is more concerned with design than with any other aspect of chemical engineering. Most of the information needed by the process design engineer is generated during the R&D phase, particularly from pilot plant data, but that information is based on small-sized equipment, whereas the production plant will contain full-sized equipment. Adapting that data is known as scale-up. This is always a mathematical technique, but the exact procedures used depend on the type of equipment being scaled up. Procedures for doing the job are available in textbooks and handbooks and may frequently be found in manufacturers' catalog and other such literature. Almost any chemical process then includes a vast array of pipes and vessels with another outside piece of equipment here and there. Open vessels are usually called tanks though. When heated, they are sometimes called kettles. Plants that process large quantities of liquid raw materials, such as petroleum refining plants, often have a number of enormous tanks arranged in an area known as tank farm. When the contents of these tanks are flammable, there are usually embankments of earth called dikes around them. If the tanks leak and the material catches fire, the flaming liquid cannot spread over the entire plant, as it did in early disaster. Piping is an important part of chemical process plant because there is so much of it. Most home piping is of small size and is put together by screw threads cut into the pipe. Screwing section of pipe together is easy to do with small sized pipe because it can be easily handled. But the pipe used in process plant generally range in size from 2 to 12 inch in diameter, and a section of such pipe may weigh many hundreds of pounds or kilograms. Large diameter pipe is put together by means of welding or pipe flanges. When flanges are used, they are usually welded to the ends of the pipe. The flanges have a ring of holes around them so that two flanges can be bolted together with a gasket in between. Flanges have two advantages. First, welding can be done on the ground or in a shop. Second, second, the pipe can be easily disassembled for inspection or replacement. The disadvantages are that the joints sometimes leak and the flanges are expensive. Welded pipe is harder to assemble because the weld must often be made while the pipe is high in the air or in awkward position. A good weld joint will not leak, and welding is a cheaper way of assembling pipe than flanges. However, the pipe must be cut and re-welded if it has to be opened for inspection of or if it is necessary to replace faulty section. Pipe is made with walls of various thickness. Thicker walls are required to carry materials under higher pressure preserved. Part of the design engineer's job is to calculate the pressures a pipe will have to withstand and to specify walls of the proper thickness. There are a number of pipe fittings used with all piping systems. When a pipe must change 90 degrees in section, a pipe elbow or a 90-degree L is implied. 45-degree Ls change the direction by 45 degrees. When one pipe joins another at right angles, the juncture is made with a pipe T. A pipe cross joins four pieces of pipe. Pipe of two different sizes can be connected by reducers or pipe reducing fittings. When pipes must be joined at a sharp angle, a pipe lateral fitting is used. As with pipe, vessels, vessels that withstand high pressures must have extra heavy walls. These are known as pressure vessels. Must be carefully designed and constructed. Failure in pressure vessels may result in explosion, with large pieces of the vessels flying around the plant. A circumstance exceedingly dangerous to personnel and destructive to equipment. Therefore, the design and construction of pressure vessels, usually defined as those containing above 15 lb slash SQ dot in dot comma 0,01 kilograms force slash SQ dot cm dot comma or 100 kilopascal is usually regulated by laws known as pressure vessels codes. Any governmental body may write its own code. In the United States, governmental body in the United States, most areas adopt the vessel code of the American Society of Mechanical Engineers (ASME), which is then enforced by governmental pressure vessels inspectors. This code defines the way in which a design engineer must calculate vessels' wall thickness and shapes, and also set up fabrication procedures to be followed during construction. Welding, for example, must be done with extreme care and skill. Generally, welders who work on pressure vessels must pass a special test and are then known as certified welders. After a vessel has been designed and built, it must pass a pressure test conducted under conditions spelled out in the pressure vessel code. Because of the complications surrounding pressure vessels, the process design engineer usually design only large or specialized vessels. Smaller ones can be purchased in standard size from manufacturers who specialize in such equipment. These vessels carry a special nameplate certifying that they were built according to the code and that they have passed the required tests. Designing process plant equipment requires more than scale-up or following design codes. It also means specifying the materials to be used for equipment. Actually, the material must be selected before the equipment is designed because the design is related to the strengths of the various material of construction. Most chemical process equipment is built from ordinary steel called mild steel or carbon steel, but many chemicals attack mild steel, causing corrosion. When this is a problem, the design engineer usually turns to stainless steel, an alloy of iron, nickel, and chromium. Some stainless steel contain other metals, such as molybdenum, that give the alloy greater strength, resistance to corrosion, or another desirable property. When corrosion problems are too severe for stainless steel, the engineer may choose alloy that contain large quantities of nickel, known as high nickel alloys. These special alloys are usually sold under trade names. Some are Estalloy, Incolloy, and Inconel, and may cost as much as several dollars a pound. Some process conditions require more specialized metal like titanium, tantalum, or zirconium. These are called exotic metals and are also very expensive. In addition to metals, the design engineer has a large number of non-metals to choose from. These include glass, plastic, graphite, and ceramics. Alone or in combination like glass-lined steel or rubber-lined plastic. The graphite used in process plant is usually impregnated with plastic and is known as impervious graphite. There are limitations to the use of nonmetals. Most are not as strong as metals, so they cannot be used for high-pressure equipment, nor can they withstand high temperatures. A process plant is usually designed in several stages after the research and development has been done and before the decision is made to build a full-size plant. A final economic evaluation made, made, must be made. Of course, economic evaluations were made before and during the R&D work, but they could be little more than educated guesses. The first time there is enough information to make a firm estimate of the cost of the plant and the cost of producing the product is when R&D is complete. The cost of the final product is based on two things: capital investment and operating costs. The first is the cost of the land, the plant, and its auxiliaries such as railroad spurs, electrical power lines, and sewage treatment facilities. Include here is the cost of the equipment, materials, supervision, labor, and design. The total of this cost, a large sum of money that must be available at one time, is the capital investment. The second, operating cost, includes the expense of running the plant after it is built, raw materials, labor and supervision, maintenance, shipping, and so on. To determine whether or not an operation will be profitable, the design engineer must calculate the rate of the return on investment (ROI) as follows: percent ROI equals net annual income minus net annual depreciation divided capital investment plus R&D cost in multiplied 100. Annual depreciation is the annual loss in value of the plant. and its equipment owing to wear and obsolescence. In the chemical process industries, it is common to require that a project have an estimated ROI of at least 20% after income tax before it will be approved for construction. Thank you.